the brief introduction, and thanks for all the presentations beforehand about real interesting topics in modern development of displays and touchscreens and the surrounding industries. I want to talk a little bit more about how to break those technologies, how to damage them, and how to prevent them from being damaged, and how to test if they are likely to not being damaged at all. So about test design and evaluation of realistic scratches and abrasion of those components. I'd like to start a little bit about who we are, what we do. So we are a German SME founded over 30 years ago, and with a headquarter located right in the center of Germany and multiple manufacturing sites all over the country. Are located still in Germany with all of our productions, but besides that, we also have sales reps all around the world, huge distributor network, and our own sales rep in Beijing in order to be globally orientated and to provide service to all of our customers all over the world. So what do? We produce, our main business branch focuses on development and production of measurement and testing devices for materials and surfaces. We also do contract testing, of course, research and development in public funded research projects and private funded projects as well as worldwide consultancy, training and distribution for our products and everything around that. So kind of a full service package as well. We serve many key industries, many key industries for us. So I just threw a bunch of our customer logos in there. Some of them you probably will recognize. Our main business branches are towards automotive industry, because of course we are a German company, and telecommunications as well. You probably will see a lot of display, touchscreen producers there. But we are widespread about all the different branches of industry. So today I want to talk about, as I introduced earlier, about how to design a scratch test, how to design an abrasion test in order to test displays, touchscreens, and basically all surfaces against or for scratch resistance and for abrasion resistance capability. And I want to do that by stepping with you through all the different steps of the test pattern design and the evaluation methods needed for that. So scratches in real life, where do they occur? Pretty much everywhere. If you just take a second or a few seconds, take a look around your surrounding, you probably will see a lot of damages on surfaces everywhere, scratches, abrasion marks. Most of them you will probably never notice directly because they don't bother you. I have an example here of an elevator, of a floor where the chair, office wheel, the scratch marks on it. But there are also other examples which might bother you a little bit more, which are a little bit more annoying to you, like the exterior paint of your car. I mean, of course, this is a pretty German example. I know car exterior painting is rated differently in other countries in Europe, but I think you got a point. What I want to mention here is that when we talk about the scratches and abrasion, nearly all of the scratches and abrasion in daily life are somehow introduced by some sort of human interaction. And this leads to the fact that they are applied with 1 to 1.5 meters per second speed. And they typically come in very long stroke length, speaking about more than 5 centimeters each. And I just want to mention, because this will become important later on, that most of the sample surfaces nowadays are polymers, since they are pretty much everywhere. Let's take a step back and take a look at the different conventional test methods that are out there in the market and are still used widely. So let's say you get a problem which you have to solve about testing the scratch and abrasion resistance of your samples, of your goods, of whatever you produce. And first approach in solving this problem is you take what you know, you take what you got, and try to solve it with those tools. So I'm pretty sure most of you have seen one of those machines in real life, or already used one of those machines, which are depicted here. And they're just brilliant for their field of application. They do what they are supposed to, and they're just fine. I mean, they run like all the time. It's great. But they were developed about more than 90 years ago for a different question, a different field of application. Because back then polymers were not so trendy, not so highly used like nowadays. They've been used for leathers or metal mainly, and yeah, for that this is completely fine. But I'd like to take you a step back and rethink about if this is still their approach, which is suitable for testing your kind of products. So let's redefine the reasonable specification for realistic test parameters of scratch and abrasion resistance tests for your surfaces and products. So first thing which comes to your mind when thinking about parameters is probably duration cycles. How long do you stress your surface? This is definitely one important parameter, and of course the load. Load has a huge impact on the test result, but I want to bring out another parameter which comes into play, especially when we're talking about polymers, which is the speed. So what you can see here is a graph showing the friction force on a sample polymer surface under varying loads on the x-axis and different speeds in different colors. And what you probably will notice is that the friction force doubles when we increase the speed on the sample surface under test by a factor of 10. And this is already at 1 Newton load, and it only gets worse. So speed definitely is an important factor when it comes to test design. I have 2 other examples I'd like to show you briefly. First, this one is on a paper with different speeds, and you probably see, I'm not sure how good the video is, but there's different spots on the sample, on the stroke length, where the tip is not in contact with the surface anymore, and this is highly speed dependent. This is what we call the water ski effect. It's like a water ski driver bumping over the water and being in contact with the water at some points, and when there's a wave, he loses contact to the surface. And this is, of course, as you know from water ski, highly speed dependent. The other example I'd like to show you briefly is this example. It's a little bit hard to see, but this is actually a transparent PMMA disc with 3 scratches on it. The black grizzle background is just supporting to make it visible. And there are 3 different scratch paths. The green one in the green circle at 20 centimeters per second, 10 Newton load, and then one where the load has been doubled, and one where the speed is higher. And all of a sudden, when the speed is increased, you all of a sudden see the scratch mark, which you have not seen before, also for higher loads. And so this is what we call the self-healing effect of polymers. And this is very specific to polymers. You don't have that, or you rarely have that in metal surfaces at all. And this is also another reason why speed is such an important parameter for testing polymers. Just want to show you a brief example about are we still here? Hello? I think it somehow broke down. Let's see if we can get back. So this is for slow scratch speed and video. I have another example here for high scratch speed. Just to take into consideration which movement looks closer to the reality. If you just think of the scratch on the car door or the office chair wheel. Just want to drop that here, leave that as it is. So yeah, just think about that. So to have the first learning here, I just want to point out speed is definitely an important parameter to take into consideration when testing non-metal surfaces like polymer, wood, or paper. Of course, additionally to the conventional parameters like load and duration and cycles. So because there's the water ski effect and there's self-healing function of different coatings. So we definitely need test methods with speeds of 1 up to 1.5 meters per second in order to simulate the real life scenarios. The other point I'd want to point out is that we have a trend from in the development of interaction surfaces from traditionally buttons and switches to non-interactive displays to nowadays fully functional surfaces with interactive displays all over the whole car and even the key, as you can see on this picture here. We've already seen this different interaction modes about how to interact with the display. I just wanted to point out here that the difference between scratch and abrasion, just because I just used them comparatively beforehand, is that the scratch is an unidirectional move, so only in one direction, typically by a sharp tip with not many cycles, whereas abrasion is a bidirectional move, so it's reciprocating with a broad contact surface and more cycles typically. So you have to make sure that when you want to test scratch or abrasion, that your movement pattern looks like a scratch or like an abrasion. Compare that to the videos before. I have a slow abrasion movie, how to test slow abrasion and how to test far abrasion. Think of using a rubber on a pencil stroke and just imagine how fast you try to rub the pencil away in order to compare that to real life. I think I can step over the 3 modes of interactions because they've just been shown from the TUM recently, so I'd go over that and sum up that besides the speed, which is also an important parameter, we have to think about the motion type in general in order to provide or to design the best realistic test pattern to mimic and simulate reality as close as possible. This is just one side of the coin. The best realistic, reproducible, comparable, calibratable test is meaningless if the evaluation you have is not sufficient. So just want to mention 3 different modes of evaluation briefly, because nowadays the evaluation still lacks a little bit of comparability. Nowadays we just use like daylight, D65 light. This is as best as we can get, and then we have comparison charts. And you have like descriptions like little visible abrasion. And this is still nowadays standard in automotive industry and in a lot of different companies or in OEM specs actually. So better way to evaluate abrasion marks is one example is water contact angle, which is a perfect measure for flat and transparent surfaces. You pay laser water contact on the sample surface and measure the contact angle. And it's widely used in the glass industry, I guess. So probably a lot of you are already familiar with these techniques. Up to our experience, the contact angle of water should be greater than 100 degree after abrasion test, and typically it will evaluate and it will proceed like that. So the longer the abrasion takes place, the smaller the water contact angle gets, and then you define a certain criteria after which you stop the test or the test is failed. Second method is 3D optical, because it should be non-destructive topography measurement tool. So which can also in that case evaluate the visual impression, so the impression for the human eye, and translate that to comparable numbers, which can be then saved, stored, compared later on. This is a perfect measure for structured surfaces. Here's a brief example on that. This is a printed control button. It looks like the top 4 pictures in that line to the human eye, and if you measure the topography, this is the lower line, you see as the abrasion proceeds that the lettering and the printing vanishes. Yeah, and I want to sum up and to conclude that, of course, you have to make sure that designing the test pattern on one hand is suitable to match the real life scenario. It should fit the right speed. It should fit the right movement type. It should fit the stroke length, load, and duration, of course, too. We need speeds up to 1 meter, 1.5 meters per second if we want to mimic real life human-induced abrasion and scratches, and we have to take a look on if we want to have one direction or reciprocating movement on the sample surface. And on the other side of the coin, we have to find suitable evaluation methods like water contact angle and 3D topography measurement, for instance, to evaluate the damage we've done to our surface before. So, and yeah, by pointing that out, I'd like to conclude and thank everybody for your attention, and meet you in the Q&A section.